All right, let's take a look at problem 10.2. So we are told that a beam of light hits the boundary between air and some unknown material at an angle of 43 degrees relative to the normal. And we are then told the reflected and refracted rays make an angle of 180 degrees with respect to each other. So the first thing I'm going to do is sketch this situation. So I'm going to have the boundary be horizontal. And I will draw my normal line, which is perpendicular to that. We have our ray coming in from air and unknown. Myra, I can't draw if you're sitting on my computer. There we go. Sorry about that. And we are told the light is coming in at an incident angle of 43 degrees. We are told there's a reflected ray and a refracted ray. So the reflected ray will go back this way. This will be the reflected. And the refracted ray will be something like that. And what we are told is that this angle right here is 103 degrees. So this is going to be my sketch. And notice that it looks very similar to a ray diagram, but this is not a full ray diagram yet because I don't have all of the proper angles labeled. I just have whatever information was given to me. So now let's turn this into a ray diagram. So there's our surface again. There's our normal line. We have the incoming ray at 43 degrees. And we have the outgoing ray. And here's where I can use the law of reflection. I know that these two are going to be equal to each other. So this is going to also be 43 degrees. And then I have my refracted angle here, my refracted ray. And I know that this angle is 103 degrees, but I don't care about that angle. I care about this angle. But if I notice, these three angles together, let me use a different color so we can see. These three angles here form a straight line. So I know that 43 degrees plus 103 degrees plus this theta 2 that I don't know, they have to sum to 180 degrees. So this is 146 degrees plus theta 2 is 180 degrees. Theta 2 is going to be 34 degrees. So now I can label these. And technically I've started solving here, but that's okay. So if this were work that I were submitting for a teacher and not recording it myself, we would have to explain how exactly we know that this statement is true. So now what we want to find is the index of refraction of the unknown material. So we've already found that the angle of incidence, or the angle of refraction, is 34 degrees, and the angle of incidence 43 degrees. So since we have both these angles, we can use Snell's law. To find the index of refraction of the unknown material. So N1 sine theta 1 is N2 sine theta 2. N1, because it is air, is 1 times sine of 43 degrees is equal to N2 times the sine of 34 degrees. So N2 is sine of 43 degrees divided by the sine of 34 degrees. And that, if I plug it into my calculator, sine of 43 degrees divided by the sine of 34 degrees, I get 1.22, approximately 1.22196, whatever, 1.22. So that is the answer that I get. So now, let's evaluate this. Is this answer reasonable? So first I can do my gut checks. 1, it's unitless, units check out. 2, how should this compare to the index of refraction of air? So I know that theta 1 is greater than theta 2. I don't know why it's 2, there we go. So that means that N2 has to be greater than N1 because that's what Snell's law tells us. 1.22 is in fact greater than 1, so this checks out. But again, this isn't a very strong evaluation because this means that I would accept any value larger than 1. And that's clearly not true. If I got an answer of like 57, that's probably unreasonable. So I can note that 1.22 is well within the region of indices of refraction we've seen before. In this class, we've never gone any higher than 1.6. I happen to know, because I am a physics teacher, that diamond, which has one of the highest, is 2.4. So indices of refraction are always above 1, but within 1 to 2. So it's greater than 1. It does fall in the region I'd expect, but I can test this. We have a simulation that we can use here. So I can just pull this in directly and verify that the angles check out. This will load. I'm going to go into this one that lets me look at the precise angles. We're going from air, and then I found 1.22. So I'm going to set my index of refraction to 1.22. There we go. And if I have an angle of incidence of 43, I should have an angle of refraction of 34. Two. Oh, I had it. There we go. There we go. So look. What I would do if then I were submitting this for credit, I would take a screenshot. And then this is my evaluation. I plug this into this simulation, and I get exactly the angles that I expect to get. With this index of refraction, this angle of incidence, this angle of refraction, it all checks out. So this really supports my answer. This tells me that I did something right. And if I had done this with the simulation and I didn't get an angle of 34 at this index of refraction, that would tell me that I did something wrong somewhere. Either my calculation of n would be incorrect, or my calculation of theta 2 was wrong, in which case my angle, or my n2 would also be different. But that would tell me that I made a mistake somewhere that I have to go back and fix. The fact that this simulation shows exactly the angles that I expect at the value of n that I calculated supports my answer. So I am confident in this solution. All right. Thanks for listening.